Hello everyone. In this video, we are going to discuss about ionic or electrovalent bond from the unit for chemical bonding and molecular structure, class 11 chemistry. You see, the formation of ionic compounds primarily would depend upon the ease of formation of positive and negative ions from the respective neutral atoms. See, metals lose electrons to form positive ions or cations. The ease of this process that depends on their ionization energy. See, the formation of ionic compounds would primarily depend upon the first one, the ease of formation of positive and negative ions from the respective neutral atoms. And metals lose electrons and they form cations or positive ions. The ease of this process that actually depends on their ionization energy. What is ionization energy? It is the energy required to remove an electron from a neutral atom. See, elements with low ionization energies like alkali and alkaline earth metals easily form cations. So, elements with low ionization energy like alkali and alkaline earth metals, they easily form cations. Now you see, non-metals, they gain electrons to form negative ions or anions. The ease of this process that actually depends on their electron affinity. So non-metals gain electrons to form negative ions or anions. The ease of this process that actually depends on their electron affinity. What is electron affinity? It is the energy released when a neutral atom gains an electron. See, non-metals with high electron affinity like halogens, they readily form anions. So, non-metals with high electron affinity, they form anions. The greater the difference in the tendency to lose and gain electrons between two elements, the easier it is for an ionic bond to form between them. Now, the formation of ionic compound that also depend on the arrangement of the positive and negative ions in the solid, that is the lattice of the crystalline compound. So, the formation of ionic compound that depends on the ease of formation of positive and negative ions from the respective neutral atoms, as well as it also depends on the arrangement of the positive and negative ions in the solid, that is the lattice of the crystalline compound. You see, once the positive and negative ions form, they arrange themselves in a crystal lattice, which is a highly ordered structure. The lattice energy, it is the energy released when 1 mole of an ionic compound forms from its ions in the gaseous state. See, the lattice energy governs the stability of the ionic compound in its solid crystalline structure. So, the lattice energy governs the stability of the ionic compound in its solid crystalline structure. A high lattice energy makes the ionic compound more stable. So, for more stable ionic compound, the lattice energy must be very high. See, the lattice energy depends on the charges of the ions, the size of the ions, etc. The charges of the ions means higher charges result in stronger electrostatic forces and greater lattice energy. Similarly, the smaller the ions or smaller ions that allow the charges to be closer together, increasing the attractive forces and lattice energy. So, the lattice energy depends on the charges of the ions as well as the size of the ions. Higher charges result in greater lattice energy. Similarly, smaller ions that increases the lattice energy. The formation of a positive ion involves ionization. That is the removal of electrons from the neutral atom. So here we have an atom M which is in the gaseous state. By removing an electron from it, it becomes a positive ion. So the formation of a positive ion involves ionization, that is the removal of electrons from the neutral atom. Similarly, the formation of a negative ion involves the addition of electrons to the neutral atom. So here we have a neutral atom X which is in the gaseous state. It accepts or gains an electron and it becomes a negative ion. See, this element M has a tendency to lose electron and to form a positive ion. This element X has a tendency to gain electrons to form a negative ion. So these two M plus ion and X minus ion, they join together, combine together and form a compound MX which is in the solid state. Okay, now you see, what about this ionization enthalpy and electron gain enthalpy? See, we have already said that this ionization enthalpy, which is actually the energy required to remove an electron from its neutral atom. Now, what about the electron gain enthalpy? See, electron gain enthalpy, it is usually represented like this: delta Eg, then H. Delta H, then here we have a subscript as Eg, electron gain enthalpy. See, electron gain enthalpy, it is the enthalpy change when a gas phase, atom in its ground state gains an electron. Or enthalpy, see, enthalpy is the total heat content of a system and the enthalpy change refers to the difference between the enthalpy of the products and the reactants. See, electron gain enthalpy, that is the enthalpy change when an electron is gained. Enthalpy change refers to the amount of heat absorbed or released during a chemical reaction or a physical process at a constant pressure. The electron gain, that process may be exothermic or endothermic. In the case of electron gain enthalpy, the electron gain process can be either exothermic or endothermic. What about exothermic process? In this process, energy will be released. Halogens like chlorine have highly exothermic electron gain enthalpies. And what about endothermic process? In endothermic reactions, energy is absorbed. That is, for example, noble gases. In noble gases, the reactions will be like that. And you see, the ionization, this ionization which is always endothermic. Ionization enthalpy is the energy required to remove an electron from a gaseous atom in its ground state to form a cation. So the result is the formation of a cation. In this case, electron gain enthalpy, the result is the formation of an anion. So ionization enthalpy is the energy required to remove an electron from a gaseous atom in its ground state to form a cation. See, this process, it is always endothermic because energy must be supplied to overcome the attraction between the nucleus and the electron being removed. So ionization enthalpy, this is actually the energy required to remove an electron. The result is the formation of a cation. This process is always an endothermic process because energy must be supplied to overcome the attraction between the nucleus and the electron being removed. See, electron affinity, it is the negative of the energy change accompanying electron gain. The term electron affinity, it is closely related to the concept of electron gain enthalpy. See, electron affinity, it is the energy released or absorbed when an electron is added to a neutral gaseous atom. Electron gain enthalpy, that is actually the enthalpy change accompanying the addition of an electron to a neutral gaseous atom. Electron affinity, it is typically expressed as the negative of the energy change. And electron affinity, it is the negative of the electron gain enthalpy. Electron gain enthalpy is delta subscript EGH. Okay, negative of the electron gain enthalpy. Okay, and you see, ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. So ionic bonds will be formed more easily between elements with comparatively low ionization enthalpies and elements with comparatively high negative value of electron gain enthalpy. Most ionic compounds typically consists of cations derived from metallic elements and anions from non-metallic elements. Most ionic compounds typically consist of cations derived from metallic elements and anions derived from non-metallic elements. For example, let us consider sodium chloride. See, so in sodium chloride, the sodium ion, that is Na plus ion, it comes from the metallic element sodium. And the chloride ion, that is Cl minus ion, that comes from the non-metallic element chlorine. However, ammonium ion, that is NH4 plus ion, it is an exception. It is a polyatomic ion because you see there is one nitrogen and 4 hydrogen atoms are there. It is a polyatomic ion that is formed entirely from non-metallic elements nitrogen and hydrogen. But it acts as a cation, that is, it acts as a cation or positive ion in most of the ionic compounds. See, the ammonium ion that can combine with anions to form ionic compounds despite not containing any metallic elements. For example, ammonium chloride NH4Cl. Okay, in this compound NH4 plus ion, that is ammonium ion, that actually acts as a positive ion or cation. Then chloride ion, that is Cl minus ion, that actually acts as a anion, that is negative ion. The compound forms a typical ionic bond between NH4 plus ion and Cl minus ion, resulting in an ionic structure. This demonstrates that ionic compounds can form even when the cation is derived from non-metals, as long as it carries a positive charge. Okay. The ionic compounds in the crystalline state that consist a highly organized three-dimensional lattice structure where cations and anions are arranged in a repeating pattern. See, this structure is held together by strong Coulombic or electrostatic forces between the oppositely charged ions, that is positive and negative ions. The specific crystal structure that forms depends on several factors, including relative sizes of cations and anions, that is the size ratio affects how ions pack together. Coordination number, this is the number of oppositely charged ions surrounding a given ion. Then minimization of potential energy, the ion arrange themselves to maximize attractive interactions and minimize repulsive interactions. That is, the ionic compounds in the crystalline state, they consist a highly organized three-dimensional lattice structure where cations and anions are arranged in a repeating pattern. For example, let us consider the pattern or the crystal structure of sodium chloride NaCl, that is rock salt. See, in NaCl, we have Na plus ions and Cl minus ions. So, you see this is the rock salt structure of sodium chloride. These yellow colored ones are the Na plus ions and these blue colored ones are the Cl minus ions. So, in NaCl, the Na plus ions and Cl minus ions are similar in size. Though it is not similar here in this picture, it is quite similar in size. That allow the face-centered cubic structure, that is FCC structure, which you will learn later. Then each Na plus ion, see, each Na plus ion is surrounded by 6 Cl minus ions and vice versa, giving 6:6 coordination number. That is, for example, you consider this Na plus ion. See, here we have one Cl minus ion, here we have one, here we have one, here we have one, here we have one, and here we have one. So 1, 2, 3, 4, 5, 6. So each Na plus ion is surrounded by 6 Cl minus ions. Similarly, a Cl minus ion is surrounded by 6 Na plus ions. So coordination number is 6 here. The result is a stable, high symmetry structure where Coulombic forces are maximized. This arrangement leads to the typical cubic crystals observed in NaCl or rock salt and contributes to the compound's high melting point and brittleness. See the rock salt structure of NaCl that is actually shown here. In ionic solids, the formation of the crystalline lattice is a highly exothermic process that stabilizes the compound even if the initial steps involve absorption of energy. Here is how it works step by step. The first one is energy absorption. The ionization enthalpy of sodium is 495.8 kJ per mole. This is the energy required to remove one electron from a sodium atom to form a Na plus ion. The electron gain enthalpy of, for the chlorine or for the change Cl gas to Cl minus gas, that is for the change chlorine to Cl minus ion, that is minus 348.7 kilojoule per mole, or you can write kilojoule mole raised to minus 1. This is the energy this is the energy released when an electron is added to this chlorine atom. See, this negative sign indicates that energy is released. So, 495.8 kilojoule per mole or kilojoule mole raised to minus 1 energy is absorbed. Minus 348.7 kilojoule per mole energy is released. So when we take the sum of these two, we can write 495.8 plus minus 348.7 plus minus becomes minus. So when you subtract these two, you will get plus 147.1 kilojoule per mole. Plus sign indicates that there is no plus sign, that means it is plus, it is understood. So this is not negative, no, that actually means that here energy is absorbed. Okay, now the second step is lattice enthalpy. See, the lattice enthalpy of sodium chloride is minus 788 kilojoule per mole, which is the energy released when Na plus and Cl minus ions come together to form the ionic crystal lattice. So Na plus ion and Cl minus ion, they both were in gaseous state. They form NaCl in solid form. Now you see, when we calculate the overall energy change means the total energy change for the formation of NaCl from its elements. That is 147.1 kilojoule per mole energy is absorbed plus minus 788 kilojoule per mole energy is released. So when we find the total, you see this plus minus becomes minus. So 147.1 minus 788, that will be equal to minus 640.9 kilojoule per mole or kilojoule mole raised to minus 1. This negative sign indicates that there is a net release of energy. That is, the process is an exothermic process. So the exothermic lattice enthalpy drives the process and compensates for the energy required to form the ions. This makes the overall formation of NaCl energetically favorable as the system releases more energy than it absorbs, resulting in a stable crystalline structure. The energy released in this process of formation of NaCl, that is more than the energy absorbed. Thus, a qualitative measure of the stability of an ionic compound, it is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species in gaseous state. So in this video, we have discussed about the ionic or electrovalent bond. I hope it is clear to you. Thank you.